The safest way to repair a power line is often to never turn it off. Right now, crews are hovering centimeters from 100,000 volts of live current, fixing transmission lines that stay energized because the grid cannot afford to lose them. This is not risk-taking. This is how modern power grids are forced to operate. The question is not why they do it. It is why shutting down is more dangerous. Grid operators do not treat high-voltage transmission lines as isolated assets. Each corridor is a node in a tightly balanced network, governed by contingency planning rules known as N-1 and N-2. These standards require the system to withstand the unexpected loss of one, or sometimes two, major transmission elements without breaching voltage or thermal limits. The calculation is not theoretical. A 345 kilovolt line may carry up to 30% of a region's bulk power. If it is taken offline, the resulting power flow is forced onto parallel circuits, which can immediately exceed their transfer capabilities. The system's only buffer is the contingency reserve, typically just 12 to 15% above peak load in most markets. Any planned outage erodes that margin, leaving the grid exposed to a second event. Operators track these margins in real time. If a scheduled shutdown would reduce the reserve below the required threshold, automated risk analysis tools block the outage request. The loss of a single corridor can trigger load shedding alerts and violate N-1 reliability, even under routine conditions. The economic impact compounds the technical risk. Congestion costs rise sharply, and the need to dispatch fast start generation can drive market prices from $5,000 to $15,000 per megawatt hour. These penalties are not hypothetical, they appear as direct charges on utility balance sheets. Because reserve margins are thin, and the system must always be able to absorb another failure, the network operates at a mathematical edge. Planned outages are not a routine option. They are a last resort, used only when all other contingencies are exhausted. The system's architecture forces maintenance to occur with lines energized, concentrating risk into highly controlled specialist operations rather than distributing it across the grid. On August 14, 2003, a single line fault in Ohio set off a sequence that blacked out large swaths of the northeastern United States and Canada. The initial loss of a 345 kilovolt transmission line forced power onto parallel corridors, overloading them within minutes. Protective relays tripped additional lines as currents exceeded thermal and voltage stability thresholds. In less than 2 hours, cascading failures darkened New York City, Detroit, Toronto, and hundreds of smaller cities. Over 50 million people lost power. Economic damage reached an estimated $6 to $10 billion, with critical services, hospitals, water treatment plants, and transit systems forced onto backup generators or shut down entirely. The blackout exposed the degree to which modern infrastructure is interdependent. Data centers, financial markets, and emergency response networks all rely on uninterrupted electricity. Even a brief loss of a single high-voltage corridor can propagate through the system, overwhelming redundancy and reserve margins. Operators in control rooms follow strict protocols to prevent such events, but their tools are limited by the physical constraints of the grid. When a line is scheduled for maintenance, the risk of a cascading failure is not theoretical. It is a quantifiable threat, with direct cost implications for every hour of lost load. Today's grid carries more critical and non-sheddable loads than ever. Hospitals and AI data centers are contractually guaranteed continuous power, often with penalty clauses exceeding $15,000 per hour if service is interrupted. The economic logic is clear. The cost of a planned shutdown, including market penalties and outage compensation, can reach millions of dollars per event. As a result, utilities concentrate risk into live line operations, accepting tightly managed human exposure as the lesser cost compared to systemic instability. A lineman working on a live transmission line relies on physics, not insulation, for protection. The conductive suit, woven from metallic mesh with resistance below 0.1 ohm, forms a mobile Faraday cage. When clamped to the energized conductor with a spring-loaded copper hook, the suit and worker instantly reach the same electrical potential as the line. With no voltage difference, current cannot flow through the body. The suit's shielding cancels external electric fields, even when the line carries over 100,000 volts. The bonding process is exact. A high-impedance voltmeter checks that the suit's bonding point matches the line to ground voltage within 2%. The clamp is applied, and a current probe measures the brief surge, typically 10 to 30 amps, until the suit equalizes. Only then does work begin. The bond must remain unbroken. Any interruption can create a dangerous voltage gradient. Air itself acts as a barrier. Dry air's dielectric strength is about 30 kilovolts per centimeter. For 115 kilovolt lines, the minimum safe gap is 38 centimeters. For 345 kilovolt lines, it is 115 centimeters. Standard clearances, enforced by OSHA and NFPA 70E, add safety margins up to 180 centimeters for the highest voltages. Precision and coordination. Define live line helicopter maintenance. The operation begins with a scripted call-out protocol. The pilot announces approach speed and hover position, while the lineman confirms readiness. Both roles are governed by a sequence of fixed cues: approach, hold, bond, contact. Each cue is delivered over a dedicated radio channel with backup hand signals. The pilot must maintain lateral drift within a 0.5 meter margin, using visual references and onboard sensors to keep the helicopter's position stable relative to the conductor. This tolerance is enforced by automated alerts, and any deviation beyond the set envelope triggers an immediate abort. The lineman's contact window is strictly limited, no more than 30 seconds per engagement. Within this interval, the lineman completes the bonding and maintenance task, while the pilot holds position against wind and rotor wash. If the lineman cannot achieve a secure connection or complete the procedure within the window, the operation is aborted, and the helicopter withdraws to a safe distance. Abort triggers are predefined, such as loss of radio contact, hover drift exceeding the threshold, or unexpected wind gusts. Each action is logged in real time by a ground-based coordinator. This control loop, call out, then action, then disengage, minimizes exposure and concentrates risk into a tightly managed interval. The system relies on human performance measured in seconds and centimeters, with no allowance for improvisation. The result is not a demonstration of individual skill, but a demonstration of engineered human control within a high-consequence environment. A planned shutdown of a high-voltage transmission line triggers a direct economic calculation in every control room. The cost of a single event, factoring outage compensation to industrial customers, market penalties, and switching logistics, typically ranges from $3 to $8 million. By contrast, a live line repair, even with helicopter crews and specialized equipment, averages between $500,000 and $1 million per incident. The decision process is codified. If the projected outage cost exceeds twice the price of live work, the system defaults to keeping the line energized. This rule is enforced by automated risk matrices that weigh real-time load forecasts, reserve margins, and contractual obligations. Demand growth and asset aging further compress the margin for error. Data centers and AI facilities now require continuous power, with penalty clauses of $15,000 or more per hour for any interruption. Over 30% of transmission assets are more than 40 years old, raising the frequency of maintenance events. Utilities face a fixed constraint. Critical corridors cannot be de-energized without incurring cascading costs and reliability violations. The economic imperative is clear. Live line maintenance is not a discretionary hazard, but a system-enforced response to the financial architecture of the modern grid. A single procedural lapse initiates a defined mechanical chain. If the bonding strap corrodes or loses contact, the lineman's suit no longer maintains equipotential with the conductor. The voltage difference reappears instantly, and if the air gap compresses below the critical threshold, a flashover occurs. At 345 kilovolts, a 15-centimeter gap is sufficient for arc initiation. Rotor wash from the helicopter can induce conductor swing, narrowing clearances unpredictably. A sudden gust may shift the aircraft or the line by more than 30 centimeters in less than a second. In one documented case, step potential across the worker's feet reached 15 kilovolts, producing a current path directly through the body. Each variable, whether bond integrity, rotor wash, or conductor motion, converts a localized error into a dangerous physical event. Protective relays are calibrated to trip at precise thresholds, typically 105 to 120% of rated current, ensuring that only a true fault or a severe imbalance can trigger disconnection. If reserve margins fall below 10%, automated load-shedding protocols cut power to non-critical circuits within seconds, stabilizing frequency and preventing under-voltage collapse. These responses are executed without operator discretion. Relay logic and preset thresholds dictate the outcome. The system is engineered to contain failures by sacrificing limited load, preserving the integrity of the wider network. Grid reliability demands maintenance without interruption. As renewable integration and demand increase, live line operations become more critical, not less. The system pushes risk to the edge, concentrating exposure in controlled hands. Infrastructure is not self-healing. It is engineered, maintained, and sustained at voltage in real time.